but I got to record. There we go. Now I'm recording before we get excited. We're working on subgroups. So if you're on Schoology, I put an electronic version of that worksheet that I handed out probably on Wednesday of last week now. So if you may have a physical copy. If you don't, there's an electronic version of it in our folder. But we're talking about subgroups, and we're about to learn. Last time we touched base about subgroups, I was just saying, like, here is big group G, and here is subset H. If we take H and it like inherits the operation from the big group, then I have a set and an operation, and it's natural to say, like, is that subset also a group under that operation? And that's the way that we're going to be proceeding today. But so far, we were just looking at things that we were like, yeah, I already learned that that was a group. This one is also a group. So yes, subgroup. And that's exciting, but that's not really why we celebrate or look at subgroups. What we're going to do is we're going to be using that concept of set builder notation when we have a big group, and then we're going to design, like in theory and practice, the way that this normally works is then we define a subset of interest to us through set builder notation. And presumably we didn't know beforehand that it was a group, and then we really want to ask that question, is it? That's the dream. And so we actually have what's called the two-step subgroup test as a mechanism for focusing our attention for proving that things are a subgroup. So moving forward with subgroups, we're going to learn what the two-step subgroup test is. We're going to see how it works. And then it is like a set of procedures that we always go through every time in order to establish if something is or is not a subgroup of the larger group G. So that's the layout of the way things are going to go. Doing all right? Ready to go? Shall we look at the two-step subgroup test? Yay. Okay. See, you can be a little.
Let's do it. Yay, let's do it.
Yay. Thank you, Nat. That's what I needed. You can be little black rectangles. It's totally cool. I get not wanting to turn on your camera, but some amount of like interaction through all the like many buttons, or like using your voice, which is a real thing. It's just helpful to me. So I know that you're not all sleeping. Anyway, cool. I also shared a link. So now I'm going to share my screen, and I'm going to head over to Overleaf here. I'm in the Overleaf document. It looks like several of you are there as well. So this is Overleaf. This is a little side story for today, but that's cool. This is Overleaf. Gotta get you all. I'm playing with my Zoom. Try to still see you. There we go. Overleaf is a website for writing in LaTeX, which is the like language that I use for creating typeset math that looks way better than Microsoft Word. It's like a programming language. I think programmers would like roll over in their graves if I said LaTeX was a programming language. It's a typesetting language maybe. But Overleaf is a free website where you can create LaTeX documents without installing any software on your computer, and you can write in LaTeX if you're wanting to just sort of get started. So I shared a link with you that I think made this all like editable. A minute ago, I think I saw a little like, there we go, there we are. So that link you can click, and then you can be in this space even if you're not seeing it on our screen like we are right now. So we have a couple of things going on in here. First of all, you can make comments anytime you're coding anything. You should make lots and lots of comments, and you use the % symbol to start a comment. Oh, we've got a visitor. Hold on. Are you just throwing your things away? Okay. We're going to do our best with my little visitor in the background. Thank you. You okay? Okay, good. He's watching Star Wars. So I'm hoping Star Wars will take him through abstract algebra. Anyway, so little % sign is for comments. Really, we could ignore all of this for a while, right, that I have highlighted. You say, the first thing you do, backslashes are how you like say, I want a command, right? We're going to be typesetting in this language. So sometimes we want to type things that we actually want to show up. And sometimes we want to say like, no, actually, this is a command in LaTeX and I need, you know, the compiler to like know that I'm using a special LaTeX word. And so you preface that with a backslash. So backslash means I am now typing a LaTeX word. And then like that's not a thing I want to appear on the screen. That's just a command to LaTeX. So you say like, basically, what kind of thing am I writing? And like a paper or just like a document in Word is just an article in LaTeX. And for now, we can ignore all of this stuff. And then like your paper has a title. And if you want a date to appear, September 2021, that's not true. Let's change it to October of 2022. That's all I wanted to say for the date. And then I start my document. And I was going to make a reference to if anybody's old enough to have ever coded in HTML, but I think the answer to that is probably not. But in HTML, and like the rule is anytime you start a thing, like anytime you open a door, you need to close the door. And the same is true in LaTeX, is that if I'm going to start a document, I also need to end a document. Whenever I start a thing, I need to end a thing. And so I start the document, I end the document. I talk in LaTeX with a backslash. I say make the title. And then I start a section and it numbers it for me. And if I hit this recompile button over here, it changed from September 21 to October 2022. And it made that little section subgroups for me. And then I could say like, hello, I am here. Subgroups are great. Hit recompile and then that should show up. Yay. Hello. Do you want to say hi to everybody?
Hi.
Hi. Yeah. You feeling better? Yeah. What do you want to tell them? Do you want to say anything or are you just coming for a hug?
I'm watching stars in the bed. It is the Force Awakens.
Yeah. Connor says hi. And there's Miss Sherry. She's waving to you.
Hi, Miss Sally.
Hi. Are you feeling better?
Yeah.
Yeah, that's good.
Hopefully we go back to school soon, huh?
Yeah.
You wanna go? Yeah, what?
You know I'm sick.
Yeah. They do know that you're sick. They all hope you feel better soon, right?
Yeah.
Okay.
I have to go back to the
That sounds great. I gotta get through my stuff real quick so I can put you all to work, or else we're gonna get lots of little interruptions. Awesome. So we're working in tech here today. Subgroups, I'm gonna say the big theorem we need here is the two-step subgroup test. And then let's say that I want to make that theorem. I have a thing up here. One of the things that happens before the document begins is I said, like, I want to create this special type of environment. I want it to say the word theorem. And when I want to reference it, I want to use the letters little thm. So this is a special shortcut I've created in tech so that I can come down here and I can say begin theorem, and then it ends the theorem for me. And then I'll type the contents of the theorem inside this little environment and it'll show it to us sort of nicely. And it says, suppose G is a group. Oh. G is a group. So what did I do? G is a mathy letter. Have you ever noticed that when you're typesetting in math, your mathy letters are kind of italics and like a different font? Like they're not standard Times New Roman. Well, LaTeX has a special environment called like math mode, and you start math mode with a $sign and you end math mode with a $sign. And anything you type in between the $signs will be typed in the way that you want to see math. And you don't need to know much more about it than that, other than like, I want the G to look mathy. And so you put your dollar signs around it, you start the math mode and you end the math mode. And the thing that shows up in between the two dollar signs will look mathy, and the other stuff will look less so. So our two-step subgroup test says, suppose G is a group and H is not equal to the empty set is a subset of G. So anything I want to look mathy is in between dollar signs. Right here, I'm in a math mode in those dollar signs. I want H to look mathy, and then I use a backslash to say, now I'm talking LaTeX. I don't actually want the letters NEQ to show up on the screen, but I want the secret command NEQ to show up on the screen. In a math environment, what do you think NEQ means? What would the EQ mean?
N is an element of Q.
Ooh,
maybe, or-
almost. Yeah, the E could be for element. How about just the EQ? Don't focus on the N part. What would EQ mean?
Equal.
Equal, exactly. The EQ is for equal and the N is for not. So what's going to happen when I use that backslash NEQ is that I'm in the math world. So LaTeX knows, like, I'm typing a math thing. I'm typing a LaTeX command because there's a backslash, and I want the not equal sign to show up. Yay. And then I wanted it to be H is not equal to the empty set. That one's real easy because it's just the word empty set. It's going to give me an empty set symbol because I put a backslash before it. So suppose G is a group and H is not equal to the empty set is a subset of G. Then if, now I covered up some things in here. I know all the commands, but there's a little button I can push. There we go. Symbol palette. Nah. There are buttons I can push. I've been coding in tech for so long that I just know all the words. I am going to enumerate some things. So I'm going to begin an enumerate environment. Tech ends my environment for me, and it gives me an item in my list. Those are all tech commands that just kind of come up naturally because I'm using a nice software editor like Overleaf. Then if H is closed, not closet, add an item, and H is closed under taking inverses, I'll say closed under dot, and H is closed under taking inverses, then H is a subgroup of G. And let's hit compile and see what happens there. And it makes me a little theorem. I can expand this, I think. I can drag it this way if I want to make it bigger, make the text smaller and the print bigger, and there are other buttons I can use, I'm sure. But look, it like formatted it like a theorem, and it didn't write NEQ in empty set. It actually gave me symbols that did that. C dot is my little dot. It's a center dot, that's why C dot. Gave me the dot symbol. It all looks so nice and mathy. I could label the theorem up here as the two-step subgroup test. Hit recompile and it should label the theorem so that we have a name associated with the theorem now. Just showing you. Tech is not a thing I'm going to force you to learn, but we have an opportunity, so we might as well use it right now. So it's called the two-step subgroup test because there are two things you need to check. In theory, if we want to show something's a group, we normally have to show 4 things. Okay? And the two-step subgroup test is cool because it's saying, actually, when you're dealing with subgroups, you only have to check 2 of those 4 conditions. You do not need to check that the identity is in the subgroup, nor do you have to check for associativity. So that's why it's called the two-step subgroup test. You only have to check 2 out of the 4 group theoretic criteria. And it gives you a shortcut for how much work you have to do, which is fabulous. Can you give me a thumbs up if you're doing okay so far? Yay, thumbs ups, thank you. Yeah, feel free, you can, if you're not doing okay so far, if you ever want to throw something in the chat, that works. If you want to just unmute and scream over me, that's also fine. It's just people generally feel less comfortable with that. So that's the statement of the two-step subgroup test. It sounds exciting, right? You're like, awesome. Like, I only have to check 2 out of the 4 things. Except it's like super way less awesome than it appears to be, right? So here's the first thing. You specifically never had to check associativity anyway. I never made you check it. And so like, really, you only had 3 things to check up until now, because I gave you a pass on associativity. One should be checking associativity, but you don't have, but like I never made you. And here's the worst part, right? The worst part is that they've just been very, very sneaky. In the statement of this two-step subgroup test, we put a condition right here. This is what it looks like in tech, and this is what it looks like over here on the screen. We've put in a condition that the set H should not be the empty set. We have to check every time we use the two-step subgroup test, we have to check the 2 things that are enumerated, but we always need to check that we've satisfied the hypotheses of the theorem. And this two-step subgroup test has very sneakily put in there a set theoretic requirement that the set be non-empty. And so that's actually a thing we have to check also. So it's called the two-step subgroup test, but we actually still have to check 3 things. And given that you were going to check 3 things before, that means it doesn't really save you any work, even though it looks like it does. And what's worse is that normally, the thing you're going to show that's in the subgroup, the easiest thing that to show is in the set is the identity element. And so they like play it like, oh, you don't have to show that the identity is in the subgroup, and you don't. That's true. But almost always you will show that the identity is in there in order to establish that the set is not empty, because that just happens to be the easiest thing to do. So it's a nice theorem, but it's less nice than it pretends to be. I don't know, what's the emoji for that? Like, seems nice at first and then is not actually nice. Like, what's the expression to make for that? That's what I do all the time. That's just my face, but alas. Okay, cool. What I think I want to do, I don't want to spend too much time because every minute that I spend is a gamble that my child will continue to be entertained. I want to do a couple of things. The first thing I want to do is spell out, like I said, criteria 1 and 2 in the theorem in words. I want to say more explicitly what they mean symbolically. And this again is on your worksheet, but it'll just show us a little bit of tech in between. Okay. So criteria 1 of the two-step subgroup test. I could show you something cool here. Okay, should we be fancy? I don't know why. Here's the thing you can do in tech, which is what makes it powerful software in addition to like the math typesetting. Like a lot of people will use it if they're writing books. It's because up here where I made this theorem, I can use the tech command label. And I can label this two-step, let's label it subgroup test. Subgroup test. That's the label. So again, I started this with a tech command with a backslash, so it's not going to write label subgroup test on it. That's an internal label for me. So the thing that shows up here in the square brackets is what I want printed on the document. And then this is like an alias that I'm going to attribute to this theorem so that I can reference it later. And so what I could do here is I can come down here and I can say criteria 1 of, and instead of typing out two-step subgroup test, what I can do is say theorem backslash reference. I want to make a reference to something I did earlier in my work. And I can hit reference that subgroup test. And it should come back in here. I think I have to do a thing. Hold on. Let's try that. Reference, like criteria 1 of this theorem tells us that. And what should happen after we compile, and I might actually have to compile 2 or 3 times, because every now with references, it wants a little bit more. Right now it says theorem 1. And then when I come down here and I say criteria 1 of, it says theorem 1. And what's cool about that is if I come in here and make a new theorem, this is Sarah's. No, Connor has a theorem. This is Connor's theorem. It is very important. Don't forget it. Okay, Connor has a theorem. We've added the theorem right here. Absolutely. Connor's theorem. So like what should happen now? Now I have one theorem and I have another theorem. When I hit recompile, it's going to rename the 2-step subgroup test as theorem 2. Because I added a theorem to my document before it, like the first theorem should be theorem 1, and then the second theorem should be theorem 2. So tech will renumber the theorems. But I do not have to come here and change anything. Like if I had typed a 1, I'd have to know that I typed a 1 there and go back and retype the 2 myself. In this typesetting language, it'll update automatically. Look. Now it says theorem 2, and I didn't have to find it and change it. Tech changed it by itself because it knew that it renumbered things. And it's going to reference the theorem no matter where I move it to in my document. So if you're typing long things, this can help you not have to find all those things and change them like by hand, which is pretty exciting. It's a cool thing about tech. That wasn't the point of what we were doing. I was writing down an equation for what criteria 1 of theorem 1 tells us. It tells us that H itself needs to be closed. This works out in symbols to if A and B are elements of H, then A dot B is an element of H. So I say element of something happened. There we go. Jerry had a guess before about like element. Like I talk about things being elements of a set, and that is a mathematical symbol. And the LaTeX word for that happens to be the word in, because in is shorter than element. So if A and B are in H, then a center dot B is in H. That'll produce element of symbol. Don't put that in your mouth.
I do it all the time.
Yeah, but don't. Look, there it is in mathy writing over there. Criteria 2 of theorem reference the subgroup test. States that if A is in H, then A inverse is in H. Subscripts are caret, like superscripts are carets. We're used to that. That's true in tech as well. And little squiggly braces are for grouping in tech. So if you put more than just one symbol up in the caret, it needs to know all the things that are in the caret, so it needs a grouping symbol. And this is what it means. So I like to state these as if-then statements because we're going to be working with proofs of the 2-step subgroup test. And when I have something stated as an if-then, when I'm doing a proof, what that means is that the if part is what I get to assume. I get to assume that the if part is true. And the then part is what I have to prove. It's right here. So we're being told when we have an if-then statement, these are the more symbolic statements of like, what do I get to assume and what do I have to prove in order to establish closure? If I want to show closure under taking inverses, what do I get to assume and what do I have to prove? That's what those symbols are. Okay. I need to be done talking soon so you all get practice with the two-step subgroup test. I feel like we should do one example altogether, right? Before we go off into groups and work on the two-step subgroup test. Feel all right? Feel like a good plan? I would prove that it works. Like, why is it that I don't need associativity and I don't need to check for the identity? I could write just the gist of it. I won't write out a big nice proof because time is tight for us right now, but I'm just going to put it as like a note. So why don't we need to show the identity is in H?
On a tablet.
Okay, hold on one second. No, I cannot put Animal Jam on your tablet right now.
When you do some,
Yeah.
look at it.
Yeah, but I can't do that right now. That's a big deal. I can't do that. You'll have to play a game you already have on your tablet, or you'll have to watch Star Wars. But you have to be just a little patient with me because I'm not done talking to them yet. Can you be a little patient with me?
Where's Miss Haley?
Miss who? Miss Haley? Oh, Miss Haley's not in this class. He's asking for Dr. Yable.
No, I'm not playing.
Except he calls her Miss Haley, so we're translating here across the board.
Oh,
Oh, Miss Jerry. You were looking for Miss Jerry. Miss Jerry, you've made a friend. She's right there. Yeah.
you need one much tablet I can get it. Put it on.
I need you to have just a little more patience with me, buddy. Can you do that? Yeah. Oh, goodness. It might be dead. Did you use all? Oh, did we put it on backwards? Oh, I bet we did. Yes, we did. The tablet cover is on backwards. Problem solving. That's why none of the buttons work. It turned on. There we go.
It was magic.
Yes. Not at all skill.
When tablet keeps the other way, it just goes down by itself. It was magic.
Now, there you go. Now you're set up, you can play on your tablet, but you have to play a game you already have.
Okay, Mama.
Okay, thank you. There we go.
And Lego do though. Now we have to find the pumpkins.
Perfect. What a great fall activity.
Yeah.
Yeah. Okay. All right. How fast can my brain go back and forth? Let's find out. All right. Why don't we have to show that the identity is an H? Well, we get to assume a couple of things. The first thing that we get to assume is that H is not empty, right? Because H is not equal to the empty set, I can not spell. There exists some A in H. So that's using the hypothesis that H is not empty. Okay. But if A belongs to H, then A inverse belongs to H, if we're assuming that these two things hold. So, but if A belongs to H, then A inverse also belongs to H. So I've used non-empty. I've used that inverses exist. There's one piece I haven't used yet. What's that? Now I have two things and both of them belong to H. If only I could combine them. I can, because of the first criteria. H is closed. Okay. Now A and A inverse belong to H, and since H is closed under our operation, A combined with A inverse belongs to H, and this is E. I'm going to compile that so we can see all the text. So the gist of the little information is if I have those three conditions, that H is non-empty, that it's closed under inverses, and then it's closed under the operation, then requiring the identity be there would be redundant, because as long as those three things are satisfied, I can pick a non-empty thing, its inverse will be there, and the combination of those two things will be there by the third requirement, and that combination of two things is the identity. So if the other things are, if those three other criteria are there, that's the reason that the identity is going to fall into that group by default. But that's my short, like, not beautiful proof version of why we end up with the identity, even when we didn't require it be there. Just a quick explanation of it. Should we do an example using the two-step subgroup test? No, for an example. Okay, what example do we want to do? That's the chain rule. You're not doing the chain rule. I bet you wish you were doing the chain rule. Let's find our worksheet for today, because I don't remember what examples I put on there. I know I did the group generated by an element there, but there are other ones. I wish we were doing the chain rule. I know that's the worst part about me teaching calc before here, is that you get to see all that stuff and be like, oh, I remember when life was like that. Can't we do that? So see. Do you want to do the group generated by G, or should we do this one all together? You don't know what's what. Let's do this one all together, the group generated by G. So let's hop on back over to the tech document in Overleaf and say, let's show that the group generated by little g, denoted by, if you want a left angled bracket and a right angled bracket, you use the words that I say are langle and wrangle. Fun talk like that. Denoted by this. And what is it in set builder notation? It's the set of things of the form g to the k, where k is an integer. Have I created the integer shortcut, or will it yell at me? You have seen that it will be red. Let's go up here. I have not, so it should yell at me when I try to do that. Let's try that. And then I'll explain it if it works. Yes, it did. So look, I got that little Z thing. One of the things that I have up earlier in this document is I loaded some packages. Use package, use package, use package, use package. So there are some words like, just like in a programming language, LaTeX will have its own like little individual words that it knows. And then there are words that it doesn't know, but it can go look up in a book somewhere. And a lot of those are math words. So we have this AMS. AMS stands for American Mathematical Society. It's one of the professional organizations for mathematicians. And the AMS has made a theorem package. And so there are some math words in there. And the AMS has also created a symbols package for other things that mathematicians might want to do. So these two packages right here are full of math words. And one of them is Math BB. The Z's that, like the Z, the N, the R, the C, all of those letters that we put with the extra line on it, that's supposed to be a bold. It's called Blackboard bold. Like when you're writing with bold, but it's on a blackboard. We're in old math school ways when we used to have blackboards instead of whiteboards. Right? When we had blackboards, that kind of writing was called Blackboard bold. And so the command to get a Z or an N or a C or an R that looks like it does when we write it on our blackboards is that I want a math Blackboard bold letter. And the letter I want is Z. So this is the command for make me a fancy Z that looks like it does when it's on the board. So this is a super interesting subgroup, the group generated by G. Let's imagine you're working in big group, capital G, big G, and you have your favorite element of that group, little g. You might say, This group is huge. This group is a monster. That's actually the name of a particular group, the monster group. That is a real group. That is the name for a real thing that has a couple million elements in it. And if you're like, that group is big, it's a monster, literally, but I have this little element inside the group and I don't want to work in this group that has millions of elements in it. I just care about this one little element. Can you build me a subgroup that's way smaller than the huge group, but it contains like my little element? That's the group generated by G. It is the smallest subgroup contained in the larger group that contains your element, little g. And that's called the group generated by G. And it's all these integer powers. Remember that we have to interpret that under the group operation of the element little g. And just in terms of like, why is that a group? Like, how does that fit right with my soul? Well, if I'm containing things like g squared, what I'm saying is I need to be able to take G and combine it with itself. I need that in order for closure. So I need G to be in the group, but I also need G dotted with itself to be in the group so that I have closure. And then once I've added G squared to the group, I need to be able to take G squared and G and combine them. And when I do that, I'm going to get G cubed. And I'm going to have to keep going in this way. I'm going to need to always be able to take G and combine it with itself any number of times in order to have closure. So that's going in the positive direction. Well, if I have G, I'm going to need G inverse, and that's G to the minus 1. And as soon as I have G to the minus 1, I need to be able to take G to the minus 1 and combine it with itself, and that's G to the minus 2. And so this pattern is going to have to exist in the other direction. I'm going to have to be able to take all negative powers of my G's. And then the only thing I'm missing is G to the 0, but I'm going to definitely need that because I always take G to the 0 and define it to be the identity. And of course I need the identity in the subgroup. So this structure of like all the integer powers of G is saying I just need closure, inverses, and identity all under combinations of G with itself. And so this thing, the group generated by G, is always going to be a subgroup, but let's prove it using the two-step subgroup test. So what other environments did I create? Aha, I created an example environment and I use EX to start an example. So let's start an example here. Begin example, and then it says end example, but I want that to come at the end here. I can write in a proof environment. That's a built-in environment. Let's use the two-step subgroup test. First, let's show that I'm going to say H is Langle G Wrangle because I don't want to type that over and over again. So H is Langle G Wrangle. Let's show that H is non-empty. I'll even do my little colon before my equals. Empty. I can spell. Can you think of one element that's probably in this thing? I mean, many things are in it. There are lots of things we could show are in the subgroup. But like in Spirit, we built this thing by saying like, little g is my favorite element, and I want the smallest subgroup that contains my favorite element, little g. So like, little g should be here, right? Little g. Note that little g is g to the first power. So little g belongs to H. So I don't have to pick the identity to show that the identity is in there. In this one, I think it's easier to show that like little g belongs to H. So the set is non-empty. Okay, so far? Thumbs up if you're doing all right. See, kind of halfway. Are there I see some thumbs up, I see some halfways. Any questions on this so far? Right. We'll see if we can trudge through it, and then we can keep practicing because that's what we need to do. Next, we show G is closed under our dot operation. That is, if A and B belong to H, then A dot B belongs to H. So the next thing we need to prove is an if-then statement. That means we get to assume this part, and we've got to show this part. So the next thing I would write in the proof is that because A belongs to H, we can write, and I want to write an equation. A is equal to something. Bringing in equations is always helpful when I'm writing proofs. So A belongs to this set. So what does that mean about how I can write A? I can write it involving G somehow, but how? Just mathematically, not techie. You don't need to worry about the tech part. I'm not doing anything too abstract algebra E. I'm writing on my little board if we need it. This is coming from, what I'm asking you about is from like way back in discrete structures land. Let me stop sharing the screen for a minute so you can see this bigger. I'm asking you about discrete structures land. Step builder notation is the thing we do there, where we say, I want to take a look at the set of little G's, and then we draw the little vertical line, and then we say some sort of rule about the G's. What this means is this has a quantifier there. It has a for all quantifier there. H is the set of all things that satisfy this rule. And that always means two things. On the one hand, it means if I know that something belongs to here, then for sure that rule must be true about that thing that you picked out of the set. That's one thing that it means. But because H is the set of all things that look like that, it's also going to mean that if you find something that satisfies the rule, then it must belong to the set. So it goes both ways. If something is in the set, then it follows the rule. If something follows the rule, then it goes to the set. So this is the structure we're going to use when I'm talking about that element A, and I'm saying I get to assume that that element A belongs to H. What that means is that element belongs to the set, then that element must follow the rule. So what was the rule on our group generated by G? When I wrote it in that set builder notation, what was the rule?
that k is an integer, or
Yes, it has something to do with an integer k and the element g, right?
mhm.
It means that the a needs to look like that g to that integer power k for some integer k. That's the rule, okay? So let's go back and write that. We can write a as g to the k for some k in the integers. So that's true about a because a belongs to the set. Then I write the word similarly. So we can write, and now you tell me, what am I going to write? B is equal to I had a thing and it applied to A, and that was because A belonged to the set. But like, I don't want to forget about B. B is also an element of the set. So that thing I did for A, I should also do for B. So how am I going to write B? What's the rule?
Would it be g to some other integer rather than k?
Yeah, exactly. Excellent. So I had the suggestion g to some other sort of integer. G to the m will work. Excellent. And I need a new letter, but we know that it's an integer. Awesome. So those are my hypotheses. On the one hand, A is g to the k. On the other hand, B is g to the m. And I want to show that A dot B belongs to my set. So just to be clear, to show that A dot B belongs to H, I need to find an integer. I'm going to use L since K and M are taken, for which A dot B is equal to g to the L. If I can do that, then I've taken A dot B and I've said that's an element of the group and it satisfies the rule, because H is the collection of all things that satisfy the rule. If that's true of A dot B, then it's in the set. So let us consider A dot B. I want to look at A dot B. I wanted to write it as g to some sort of integer power. I should probably use my hypotheses. So what should I put on the other side of this equal sign? I have A dot B and I want to have all of these like equal signs until I end up with like a g to the L. So now I'm just kind of hinting there. What could I do as a first step?
Maybe g to the k dot g to the m.
That sounds lovely. Absolutely, Iman. Let's say B is equal to g to the k combined with g to the m. Let's use that information that we just asserted about what A is equal to, and let's use that information about what B is equal to. I'm going to leave it with the blank equal sign. We'll see what tech does there. So we're missing this one piece. I have a g to the k dotted with a g to the L. Sorry, g to the m, my mistake. How can I combine those to get a single g to the something? Can I do that? What is g to the k dotted with g to the l? I have some exponent rules, right?
K plus M.
Exactly, k plus m. Awesome. That is equal to g to the l for l equal to k plus m. And we just note that k plus m is an integer because the integers are closed under addition. And we assumed that both k and m were integers. So there you go. I took their dot and I combined them and I showed that it had the property that it needed. So we've established closure. So to show that H is closed under inverses, let A be in H. And we can even use the same notation so that A is equal to G to the K for some K in the integers. We need to show that A inverse is G to the L for some L in the integers. Any guesses for what L is going to be? Might be hard in the typesetting because the 1 and the L look really similar. No, I can like maximize this somehow. So A is G to the K. Any guesses for what A inverse might be? Using that hypothesis somehow? Type your guess in a private chat to somebody else in here, like you would elbow them in class so that you don't have to say it out loud, right? If you don't feel comfortable with it, like find somebody and be like, my guess is this. And I won't even see it. And then when that other person is like, yeah, that's what I thought too, then you're like, yay, now I feel confident and I'll say it out loud or I'll type it in a public chat. I have literally no problem waiting you out in silence for the next 8 minutes. If I have to. But I hope we don't have to. Come on. We can all help each other out.
So as a guess for breaking silence's sake, be g to the negative k.
There you go. See, that's it. That's all there is. We didn't need to be scared. Thank you, Eamon. That worked perfectly. Yeah. A inverse is going to be g to the minus k. That's what the L is. L is negative k. That's it. And why is that? If you wanted to see why that is, negative k works here. Since g to the k combined with g to the minus k by our exponent rules is g to the k plus negative k, which is g to the 0, which is the identity. So g to the minus k is the thing that I can take and I can dot it with g to the k, and I get to the identity. And that means that this thing right here is the inverse of this thing right here. So that's it. That's the way that these things go. This structure of what I have typed in here for you, of first show me that it's not empty, then show me that it's closed, then show me that it's closed under inverses. That is the proof structure every single time we do a two-step subgroup test. And it is like a very templated thing. So it's another thing that it's sort of nice that we're typing, right? You could copy and paste the structure of this proof for every single two-step subgroup test you're doing. It's like, next we show G is closed under C dot. That is, if AB is in H, then A dot B is in H. Because A is in H, we can write A is equal to whatever the property is. Similarly, B is in H, so we can write B as whatever the property is. Like, you literally just need to make these tiny tweaks to this template. And this proof is going to work every single time. So this is your structure. And so it's a very repeatable process. And in fact, I'm going to have you repeat it with various examples. So we probably won't have time for it today. I think it's probably best to just come in on Wednesday and start fresh. But we've done our group generated by example. We have a couple other ones we're going to do. What I would say is that I'm going to end the class by putting you in a breakout room where you can like finally talk to other people and say, think about example 2. Example 2 right here. We could prove that the things that have like integer power of 2 determinants inside of GL, this should say NR, I guess, is actually a subgroup. That's a thing we could do. Otherwise, what we're going to do on Wednesday is I'm going to put you into groups and I'm going to have you look at these things that are called the center and the centralizer. And we can talk more about them on Wednesday. I'm going to have you proving that those things are subgroups. So actually, I'm not going to put you into, I mean, you can all chat. I could like, I guess I can't leave because I'm in charge of the Zoom meeting or whatever. But like, if you want to talk to other people, you can talk to other people in the chat right now. But I feel like with 4 minutes left, there's probably not time to have a thorough conversation about any of the other examples in there. So I'm happy to just give you your 4 minutes if need be for today. Anything else you want to talk about?